All right, this is the extra examples from the 3.1 notes, starting with number 2. It says find the critical numbers of the following function. Remember, we find the critical numbers by finding the first derivative and setting it equal to 0. So f prime of x here would be 2x minus 1 using the power rules. And then if we set that equal to 0, we get a critical value of 1/2. Okay, let's look at the next example. So that was just the critical number. If we're trying to figure out if a function is increasing or decreasing, we need to look at the derivative again, but we need to look at a sign chart to figure out what's happening on each side of those critical numbers. So we need to take the derivative of number 2 here in this group, and it's going to be a little bit more difficult. You could think of this one of two ways. You could try to do a quotient rule, but since the bottom is a monomial, I think I'm going to just split this up into two separate fractions and reduce them. You cannot do that if your bottom is a binomial or bigger. So then this would just be x squared, and this one I can actually think of x to the negative 2. So then I'm going to take a derivative of that, and that would be 2x and then minus 2x to the negative 3. Or we could rewrite that as 2x minus 2 over x cubed. If we get a common denominator, we would multiply the top and bottom of the first fraction by x cubed, which makes the top an x to the 4th. And I would have 2x to the 4th minus 2 over x cubed. So that's my derivative. Now we want to figure out if we set that equal to 0, what would that look like? So when you set this equal to 0, you have things going on. You have something that's going to be the top. When does the top equal 0? And when is the bottom undefined? Because both of those things can produce critical values. The bottom is pretty easy here. If you put in a 0 there, you're going to be dividing by 0. So x equals 0 is an undefined value. For the top, I would factor out a 2. And then this factors again, so that would be x squared plus 1 and x squared minus 1, which is going to factor again into 2x squared plus 1, x plus 1, x minus 1. Now the x squared plus 1, remember, is an imaginary solution, so that doesn't give us any critical values since critical values have to be real numbers. So x equals negative 1 and x equals positive 1 are the critical values from the binomial that factored all the way down. So we have 3 critical values, so we'll want to make a chart. So I'm going to come over here, and we want to place those critical values across the chart from least to greatest. So if we can figure out if we're increasing or decreasing. So this is negative 1, then 0 for the undefined value in the derivative, and then 1. So the two top parts, remember, that's when we equaled 0, and the bottom was when we were undefined. So we pick a test value in each region. So remember, this is negative infinity to negative 1, negative 1 to 0, 0 to 1, and 1 to infinity. Something less than negative 1 would be negative 2. Something between negative 1 and 0, I would use negative 0.5. Something between 0 and 1, I would use positive 0.5. And then bigger than 1, I would use 2. So then we want to plug each of those into the derivative to see if it comes out positive or negative. If the derivative comes out negative, then we know that this is a decreasing slope. If the derivative comes up positive, we know we have an increasing slope for our tangent. So that tells us what the function's doing. So f prime of each number, if we do f prime of negative 2, that's going to give us negative 2 to the 4th is positive, and it'll be 16 times 2 is 32, minus 2 is 30, so it's positive on top, but negative 2 cubed is negative 8. So positive over a negative, just looking at my fraction, is a negative overall. So this is a decreasing interval. So negative 0.5, you'll want to use your calculator probably when there's decimals involved. You may want to use your calculator for all of them. So we're doing 2 times negative 0.5, and that's to the 4th power. Oops, I don't know if that worked or not. Nope, it deleted it. So hang on, 2 times 0.5 negative to the fourth, then minus 2. I'm just plugging it into my derivative right here. Then divided by parentheses 0.5 negative cubed, which is going to be negative. That's going to come out positive overall. So this one comes out positive. If we plug in 0.5, we end up getting a negative again. And if we plug in 2 to this, we get a positive. So remember, when you do this part right here, you're just plugging your numbers, your test values into your derivative and seeing if it comes out positive or negative. So this is decreasing, then increasing, then decreasing, and then increasing. So if we had to answer where are we decreasing and where are we increasing, we're decreasing on negative infinity to negative 1, unioned with 0 to 1. I'm just grabbing those from the columns. We are increasing from negative 1 to 0, unioned with 1 to infinity. So these are intervals. Okay, so, and I believe that's all we needed for that one. Let me double check my directions. Yeah, find the open intervals on which it is increasing or decreasing. So let's look at number 4. Number 4 is just a polynomial one, so this one shouldn't be as bad. So the derivative of this would be 3 times 3 is 9, x squared. 2 times 12 is 24, then x to the first plus 15. We will need to factor this. They're all divisible by 3. So I'm going to pull a 3 out. If it's not factorable, or if you don't want to waste time factoring, so people don't, you could plug it into the quadratic formula. So when we set this equal to 0, the 3 out front really doesn't matter anymore, but we do need to try to factor that. So 3 times 5 using factor by grouping is 15. Factors of 15 that make 8 when you add them is 3 and 5. So we remember expand the middle. So this is 0 equals 3, parentheses 3x squared plus 3x plus 5x plus 5. You factor by grouping here. So this would be 3x, x plus 1, plus 5, x plus 1. So I get 0 equals 3 times x plus 1 times 3x plus 5. And then we set those equal to 0. The 3 doesn't give us any answers, but this would be negative 1. And the other one would be negative 5/3. Hang on just a second. There we go, it stopped. So then we set up our chart over here. And negative 5/3 is actually the smaller of the two. And then we have negative 1. So this is the interval negative infinity to negative 5/3. This is the interval negative 5/3 to negative 1. And this is the interval negative 1 to infinity. Something bigger than negative 1 is 0. Something between, now negative 5/3, you'll probably want to turn it into a decimal to figure out what's in between. So that's going to be negative 1.6. So this, we could use negative 1.2 here as an interval. So negative 1.2. And then less than this, I would use negative 2. So make sure your numbers you're picking are in your intervals or they don't give you any information that's useful. So when we plug in negative 2, so we have, let's just plug it into our derivative, which is right here, 9x squared. So 9 times negative 2 squared plus 24 times negative 2 plus 15, so remember plugging it into the derivative, is positive 3. So this comes out positive. Let's plug in negative 1.2. So 9 times, parentheses, 1.2 needs to be negative, squared, plus 24 times a 1.2, that is negative, and then plus 15 is negative 0.84, so this ends up negative. 0 is really easy, it just comes out as positive 15. So this is increasing, decreasing, increasing. So I'm increasing on negative infinity to negative 5/3, unioned with negative 1 to infinity. And I am decreasing on just negative 5/3 to negative 1. So analyzing this derivative tells you a lot about how the regular function is moving. So that's the end of the 3.1 video.